Have you ever wondered how we know what's really in your water? Well, today we're going to solve a chemical mystery. How do scientists actually measure things that are completely invisible? Let's dive right in.
I mean, think about it. It's a simple question, but it has some pretty huge consequences. You can't see the calcium in your milk that helps build strong bones. Or, and this is way more worrying, the lead that might be in your tap water. So, how in the world do we measure the invisible? The answer is, absolutely critical for keeping our food safe and our environment clean.
So the scientific field that tackles this whole problem is called analytical chemistry. You could think of it as kind of the forensics department of the science world. It gives us the tools to, dust for fingerprints at a molecular level and figure out exactly what's in, well, pretty much everything.
Now, analytical chemistry really has two main jobs. The first is just figuring out what's there. Is this lead or is it iron? But today we're really going to focus on the second and honestly the trickier question, exactly how much of it is in there.
So how do we count something we can't even see? Well, one of the oldest and frankly most clever methods is called titration. At its heart, it's a way to count molecules almost one by one.
Okay, so here's the basic idea. Just imagine you have a jar full of invisible marbles, and you really need to count them. What you could do is start dropping in red marbles, one at a time, that you know will stick to the invisible ones. You just keep adding those red marbles until you run out of invisible ones to stick to. Then, by counting how many red marbles you used, you know exactly how many invisible ones were there in the first place.
In a real lab, it looks something like this. The unknown sample, that's our jar of invisible marbles, is sitting in the flask. We add our red marbles, which is just a chemical we know everything about, from that long glass tube called a burette. The exact moment we've added just enough is called the equivalence point. Then a little bit of quick math, and boom, we have our count.
And here you can see the classic setup. That long tube is the burette. And it's a surprisingly simple piece of equipment that's been a total workhorse in chemistry labs for over 100 years. It's pretty low tech, but even in an age of supercomputers, it's still incredibly effective.
Now, to make this whole thing work with metals, you need a very special chemical. So, let's meet the hero of our story, a molecule called EDTA. An EDTA has a kind of superpower. It acts like a microscopic claw.
See, EDTA is what's known as a chelating agent, and that word chelate literally comes from the Greek word for claw. These molecules are basically designed to do one thing really, really well: find a metal ion and just never let go.
And this slide shows that claw in action. That little M you see in the center, that's our metal ion. The EDTA molecule just completely surrounds it, grabbing it from 6 different points and locking it up tight in a secure little chemical cage. And here it is. This is the secret to why this whole technique works so perfectly. One EDTA molecule grabs exactly one metal ion. It's a perfect 1-to-1 ratio every single time. And that means if we can just count the EDTA claws we used, we know exactly how many metal ions were in our sample. It's really as simple as that.
Okay, so we've got our molecular claws, and they're ready to grab all the metal ions. But there's a big problem. This is all happening invisibly inside the flask. So how on earth do we know when we've caught the very last one? How do we see the finish line?
This really is the critical moment, isn't it? If we stop adding the claw too early, our count is wrong. If we stop too late, our count is wrong. We need some kind of chemical flare gun to go off, signaling the exact moment the job is done.
The solution is just pure chemical genius. We add a special dye, and we call it an indicator. Think of it like a plant that changes color depending on the kind of soil it's in. This dye also grabs onto metal ions, and it has one color when it's holding a metal and a completely different color when it's not.
So, here's how it all plays out. The indicator dye, yeah, it can hold onto the metal. But our EDTA claw has a much, much stronger grip. It's basically a chemical tug-of-war that the EDTA is always guaranteed to win.
Okay, this is the magic moment. At the start, the solution is red. That's because the indicator dye is holding on to all the metal ions. Then, as we add the EDTA, it first grabs all the free metal ions. But once those are all gone, the super strong EDTA claw comes along and just rips the very last metal ion away from the indicator. The second that happens, the indicator is now free, and it instantly turns blue. That's it. That's our finish line.
So that color change is our visual cue, right? But for real precision, chemists turn that visual into hard data.
And by plotting the reaction as it happens, they can create something called a titration curve.
This graph here, it tells the whole story of our titration. Along the bottom, that's how much EDTA we're adding. And going up the side is how much free metal is left in the flask. So at the beginning, as we add the claw, the metal concentration goes down slowly. But then, look at that huge, sudden drop right in the middle. That's our finish line. That's the equivalence point, where the metal just suddenly runs out.
So this curve, it really tells a three-act story. Act 1, we're adding EDTA. The metal concentration is dropping steadily. Act 2, the climax. That huge vertical drop is the exact moment we run out of metal. And then, Act 3, the aftermath. Now we're just adding extra EDTA to a flask that has no more metal left for it to grab.
But, of course, there's a catch. Our molecular claw works best only under the right conditions. You can think of it like a tool that can get a little rusty. The acidity of the solution, what chemists call pH, can actually change how well that EDTA claw works. As you can see here, you have to get the pH just right for the claw to have its strongest grip.
And this is exactly why getting those conditions right is so important. Look at that top curve. See, when the pH is perfect, we get a nice, sharp drop, a really clear finish line. But as the pH changes, that drop gets smaller and kind of mushy. It's much harder to tell exactly when you've crossed the line. So that's why chemists will carefully control the conditions to make sure their results are super accurate.
So, okay, this is a pretty cool process, but does it actually matter outside of the lab? Oh, absolutely. This technique is a workhorse of modern chemistry, and it's used every single day to solve very real-world problems.
Honestly, its applications are everywhere. Ever heard of hard water? Well, titration can tell you how hard your tap water is. Are the metal levels in a patient's blood getting dangerously high? Titration is the test for that. Does that vitamin supplement actually have the right amount of zinc? Titration is what provides the quality control. It is just a fundamental tool in countless fields.
So the next time you look at a glass of water, just remember the incredible chemistry that allows us to understand exactly what's inside. It's really amazing to think that a few clever drops and a splash of color can reveal so much about our invisible world. It kind of makes you wonder, right? What other huge problems can we solve with just a simple, elegant idea?